Assalamualaikum warahmatullahi ta'ala wabarakatuh and a very good morning. Welcome to the second part for the topic electronic configuration and atomic orbital. From the previous part, you already learned about how to draw the orbital diagram, how to write down the electronic configuration. Now we move to the next subtopic, which is the ways to express electronic configuration. There's several ways to express the electronic configuration. The first one about the SPDF notation. This SPDF notation you already learned from the previous part, where for example from when we to write down the electronic configuration for sodium. Okay, you must using the number of proton or number of electron that they have. Okay, for example, for sodium, number of electron is 11. So we start with 1s2, 2s2, 2p6. So which means you already use 2 to 6, 10 electrons. Now only remain 1 electron. So you just fill it with, after 2p is 3s1. So this is how to write down the electronic configuration in SPDF notation for sodium. Next example for potassium with number of electron 19. So we start with 1s2, 2s2, 2p6, 3s2, 3p6. So which mean you already use 1 to 6, 10, 18. Only one left. So after 3p is 4s1. Okay, 4s1. So this is the electronic configuration of potassium in SPDF notation. And the next one is iron with 26 electron. So as usual, kita start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then after 4s we continue with 3d. So before we fill up the electrons, so we can count how many electrons we use already. 10, 20. Okay, 20 until 4s. So which means remain 6 electrons. Just fill into the 3d orbital. So you must remember, for d orbital, it can fill up with 10 electrons maximum. D orbital. Okay, s orbital 2 electrons, p orbital 6 electron, d orbital 10 electrons, and so on. Alright, so this is how to write down the electron configuration using SPDF notation. Next, we move to the another ways to write down the electronic configuration by using a noble gas core, which mean we use the condensed electron configuration by using the element of group 18. Okay, element of noble gas group. Okay, helium, neon, argon, krypton, xenon, and radon. So which mean from this one you need to know. Okay, you need to remember the number of electron for each element, because this is important for you to use the condensed electron configuration. So if you can see, for this is the electron configuration when you write down for the noble gas elements. Okay, noble gas element. So by using the noble gas elements, so you can write down. Okay, so you can simplify or condense the electron configuration like this one. For helium, this is for helium, and then for neon, for argon, for krypton, xenon, and radon. So let's say we do the examples how to use the condensed electron configuration. Let's say we have the sodium. Okay, sodium. So for sodium, this is the electron configuration, the simplest electron configuration, how to write down using the SPDF 1s2, 2s2, 2p6 and 3s1. So if you can see, for the blue one, okay, 1s2, 2s2, 2p6, it's similar with the electron configuration for neon, which is neon have 10 electrons. So which means you can rewrite the electron configuration by using the condensed electron configuration like this one. Since this one is for neon, so which means we can change the electron configuration for this part into neon. So which means you can either write down the electron configuration using the SPDF notation or using the condensed electron configuration by using the notation of noble gas, okay, that related to the electron configuration. Since in this electron configuration it contain the neon electron configuration. That's why we can write down or rewrite the electron configuration like this one, neon 3s1. So this one still remain 3s1. We need to write down as usual for 3s1. Another example for calcium like this one. Okay, so this is the normal electron configuration using SPDF notation. And then if you can see this part, okay, the blue part, it indicates the argon electron configuration. Argon electron configuration with 1 to 16 electron, okay, 16 electrons. So which means from this normal electron configuration, write down the electron configuration, you can rewrite the electron configuration or simplify it using the condensed electron configuration like this one, argon for S2, argon for S2. So which means it include the electron configuration for argon, and then this is the remain notation for the electronic configuration. Okay, so which means so you need to remember the electron configuration for the noble gas if you want to use these types of a method to write down the electron configuration. Another example for silicon. So let's say this is the electronic configuration for silicon. So which means if you can see here, it contains the neon electron configuration. Okay, 1s2, 2s2, 2p6 is neon. So after that, after you use rewrite and then just write down the neon like this one in the bracket, then for the remaining one you just write down back without changing anything. So you can rewrite the electron configuration for the silicon as neon 3s2, 3p2. This one. Another example, vanadium. Okay, so for the vanadium, this is the electron configuration using the SPDF notation: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d3. And then inside the electron configuration, it contains the noble gas electronic configuration, which is the argon. Okay, 16 electrons. So from the SPDF notation, you can rewrite the electron configuration using the condensed electronic configuration, and then the blue part you just change into the argon 16 electrons, and then for the remaining one you just write down back without changing anything for S2, 3d3. Alright, so this is how to use the condensed electronic configuration. Next, about the orbital diagram, this is how to draw the orbital diagram. Okay, you can draw the orbital diagram in the boxes. Okay, from the previous part, I already tell you how to draw the electron configuration. Either you can use the line or the circle one or in the box. Okay, in the box. Okay. So, if you want to draw the orbital diagram, first of all, you need to make sure all boxes should be labeled. Okay, all boxes should be labeled. For example, we do the example. Okay, for example, we do the orbital diagram for nitrogen. Okay, for nitrogen, 1s2, boxes for 1s2, and then 2s for 2s boxes, and then 2p boxes. Since 2p have their three houses, okay, for p orbital, as if you can remember lah, okay, for p orbital have three boxes. Okay, for s orbital only one line, okay, one house lah. Okay, I call it house. For s orbital, one house. P orbital, three houses. And then d orbital contain 1, 2, 3, 4, 5 houses. Each houses can fill up with 2 electrons only, either positive, half positive, and half negative. Alright, so if you want to draw the orbital diagram, you need to label each of the houses, okay, without mention the number of electron. So how to fill up the electron configuration? Using the 3 rules, okay. The Aufbau, okay, we use the Aufbau to rearrange the ascending order, and then Hans rule and Pauli exclusion to fill up the electrons in the houses of the orbital. First of all, we need to fill up the 1s orbital. Okay, this one, half positive, half negative. After fill up the 1s, we continue with the 2s orbital. Okay, so from the until 2s orbital, we already used 4 electrons. Okay, 4 electrons. So which means since nitrogen have 7 electrons, so it remains 3 electrons. So which means the 3 electron will be in the 2p orbital. So we need to fill up 1, 2, and 3 orbital. Okay, 3 orbital. This is how to write down or to draw the orbital diagram. Okay, so boxes of the same energy are put together. This one, the same energy, which mean for example 2p, okay, 2p orbital. In 2p orbital, as I said, if you can see, contains 3 houses. So which mean we need to if you use the boxes, you need to write down or draw the boxes like this one, okay, put together, not like this one. This is round. Okay, this is round. Another example, sodium. Okay, this is the electron configuration. So to draw the orbital diagram, since I like to use the line one, okay, kita boleh buat this one, 1s, 2s, 2p, and 3s. 1s, 2s, 2p, and 3s. So okay, 2p, 1, 2, 3, 4, 5, 6, and 3s1. So this is how. So the tips is, if you mention the electron configuration in orbital diagram like this one, you are wrong. Okay, because this is not the to write down the electron configuration, but this is how to draw the orbital diagram, so without the number of electron. Okay, how about the calcium? For calcium, okay, 1s, 2s, 2p, 3s, 3p, and 4s. For 1s, 2s, 2p, 3s, 3p, and 4s. So we start to fill up with the electrons. And 4s with 2 electrons. So this is how to draw the orbital diagram for calcium. Alright, so far so okay. Okay, next example, using the silicon. So you already know the electron configuration of silicon right here. And then now how to draw the orbital diagram. As I said, if you want, let's say if I want to use the box style, okay, so we start to draw the box first. 1s, this is 2s, 2p, since it has 3 houses, so we draw 3 box, and then 3s, 1 box, 3p, 3 box also. So we label the houses using its orbital, 2s, 2p without the number of electron, 3s and 3p. Next, we start to fill up the box with the electrons. 2 electrons, 2 electrons, 6 electron, and then this one 2 electron, and then the last one, since it has 2 electrons only, so we just draw like this one. Okay, so this is the correct way to draw the orbital diagram for silicon. If you draw the 3p like this one, 1 and 2, you are wrong. Okay, so which means this is not the right way to draw the orbital diagram using the principles of Hans and Pauli. So you must singly fill up the orbital first, then baru pair dia. Okay, so that's how to draw the silicon orbital diagram. The next example is vanadium. Okay, so for vanadium, if you want to use the line lah, I like to use the line simple. 1s, 2s, 2p, 3s, 3p, 4s, and 3d. Okay, 1s, 2s, 2p, 3s, this 3s, 3p, 4s, and 3d. So we fill up the electrons, 2 electron, sorry, okay, for S and 3d, since it only has 3 electrons, so we just fill up the orbital with 3 electron, 1, 2, and 3. So that's how to draw the orbital diagram for vanadium. Okay, next, another subtopic related to the special case for certain element. So which means in this subtopic, I will show a special case to draw the electron configuration, to draw the orbital diagram and to write down the electron configuration for certain element. Okay, the first element is chromium. So for chromium, if we follow the normal way, follow the 3 rules of Bohr, Hans rule, and Pauli, then you will get the electron configuration is like this one: argon, 4s2, and 3d4. And then if you draw the orbital diagram as usual, you will get the electron orbital diagram like this one: 4s2 and 3d4. However, a special case for chromium, one of electron from the 4s2 will arrange itself and it will give the electron into 3d orbital. So which mean when it the arrangement occurs, okay, in the 4s and 3d orbital, then you will get the orbital diagram for chromium is just like this one: 4s1 and 3d5. Okay, so the 4s orbital will only have 1 electron and then another 1 electron, it will give to 3d orbital to make sure the chromium have the half-filled 3d orbital. So for chromium, if you want to write down the electron configuration for chromium, is just like this one: from AR 4s2 3d4 into 4s1 3d5, since it already do the arrangement in the electron for s orbital and 3d orbital. So why this is happen? Why the chromium have a special case in the way to write down the electron configuration and to draw the orbital diagram? This is because the chromium, the arrangement of electron between 4s and 3d in order to achieve the half-filled orbital. Okay, the half-filled 3d orbital, because the half-filled 3D orbital will give the extra stability to the electron arrangement, of the chromium. That's why one electron from 4s, it will give to the 3D orbital to give the half-filled 3D orbital. What do you mean with half-filled 3D orbital? Remember, d orbital, okay, the full d orbital, it will give 10 electrons. Half-filled orbital, okay, half-filled orbital, it means that half-filled d orbital, it means that it give only 5 electrons. Okay, so which means this half-filled orbital will give an extra stability to the d orbital. That's why it will do the arrangement from 4s to 3d. So this is how, okay, this is how to write down or to draw the electron configuration for chromium. Okay, so as I said before, the energy needed to promote an electron from 4s to 3d is more competenced by the energy released from the formation of the half-filled d orbital. So this is the key point when in exam kena tanya pasal soalan ni. So mungkin dalam soalan exam dia tanya, why the arrangement of chromium have half-filled 3d orbital? Why? Kenapa dalam chromium ada half-filled 3D orbital and 4s just give only one electron? Because of what? Because of half-filled 3D orbital will give the extra stability to the arrangement electron in the chromium compared than the normal one. Itu jawapannya. Okay, so next we move another element which has the special case in order to write down the electron configuration and to draw the orbital diagram, which is the copper. Okay, so in normal way, okay, you can write down the electron configuration for copper as argon, 4s2 and 3d9. Then if you draw the orbital diagram, then you will get like this one. However, due to the fulfilled orbital of 3d, okay, the one electron from 4s, it will arrange itself and it will transfer into the 3d orbital. So then you will get another orbital diagram for the copper like this one, for S1 and 3d10. Okay, and then you can write down the electron configuration for copper as argon for S1 and 3d10. Compare then the normal one for S2 3d9, then it will change to for S1 to 3d10. Okay, why this is happen? Because of the 3d orbital in copper. Okay, it will give the full filled 3d orbital, because the full filled 3d orbital has give the extra stability to the arrangement of electrons in the copper. That's why this is due to the symmetrical distribution charge. That's why in copper in copper, to write down the electron configuration, disobey the Hans rule orbital, the Hans rule lah kan, okay, the Hans rule. So this one same as the previous lah. So maybe dalam exam dia tanya lah, mungkin dia tanya why in copper has a special case in order to draw the electron configuration. Okay, in order to draw its electron configuration. So Bila dia tanya macam tu, kamu boleh jawab like this one, okay, using this one. Because in copper, the 3D orbital give the full field electron, okay, the full field 3D orbital, which will lead to the extra stability to the electron arrangement in copper due to the symmetrical distribution of charge. Okay, so fulfill D orbital, dia ada 1, 2, 3, 4, 5, 10 elektron, 10 electrons. Oh sorry, jenjang. Okay, and half fill orbital, for half fill D orbital, you will get like this one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Half fill orbital. 10 electrons for full fill. 5 electrons for half fill D orbital. Okay, remember that one. Next, about silicon. Okay, so for silicon, okay, the 3s, okay, if you can see from the previous slide, okay, mungkin kalau kamu fikir secara logik, kenapa silikon tidak berlaku macam tu? Sebab dalam silikon dia ada 3s dengan 3p. Maybe dalam 3s ni mungkin kenapa satu 3s elektron ni tidak berpindah kepada 3p orbital untuk mendapatkan half fill. Okay, untuk dapatkan half fill p orbital. Kenapa tidak berlaku macam tu? Okay, untuk silikon ni, kalau kamu buat macam ni, kamu akan silap. Okay, kamu akan silap untuk silikon. Sebab untuk silikon, okay, because of the 3p and 3s orbital, the energy differences between 3p and 3s orbital sangat tinggi berbanding dengan 3D dengan 4s orbital. That's why dia perlukan banyak energy, sangat banyak energy, which is it will make the process is impossible. Okay, it's impossible. That's why the electron, that's why untuk case silicon dia tidak akan berlaku dekat sini. Perubahan ataupun arrangement of electron tu cuma berlaku pada 3D and 4s orbital only. Okay, saya boleh bagi contoh lah. Contoh kan dia punya energy differences. For example, ini adalah 3s orbital. And then ini adalah 3p orbital. Berbanding dengan 3D dengan 4s, ini 4s orbital and then 3D orbital. Ini yang kita katakan the energy differences. Kalau kamu tengok antara 3s dengan 3p sangat jauh dia punya beza berbanding dengan 4s dengan 3d. That's why the arrangement of electron antara 4s dengan 3d ni boleh berlaku in case untuk achieve the half fill orbital or full fill orbital only. Okay, that baru akan ada berlaku the arrangement ataupun the transfer of electron from 4s into 3D. Okay, however in 3s and 3p tidak akan berlaku the arrangement of electron because of what? Because of the energy differences between 3p and 3s is quite high. That's why the process is very impossible lah untuk berlaku. Okay, alright, next we move into another main subtopic, which is the category of electrons. First, I would like to explain about the outer shell versus inner shell electrons. Okay, what is the outer shells and inner shell electrons? Let's say, example, we have one example. We take oxygen. Dekat oxygen, dia ada 8 protons, neutrons and 8 electrons. Then we just simple drawing the position of the nucleus and electrons. Okay, so based on the drawing, dekat tengah-tengah ni kita namakan dia sebagai nucleus. Dekat nucleus have proton plus neutron, and then dekat luar nucleus surrounded by the electrons, which is located in the shell. Okay, dekat shell tu ada dua jenis shell. Okay, two types of shell. The first shell is inner shell. Inner shell means that shell yang berada dekat dengan nukleus dan berada di dalam. Okay, okay, berada di dalam ruangan of the shell. Itu kita namakan dia sebagai inner shell. And outer shell bermaksud shell yang paling luar, okay, the outer shell, the outermost shell. Okay, itu namakan outer shell. Dekat inner shell and outer shell, of course, ada elektron. So, elektron yang located pada inner shell, kita namakan dia sebagai inner electron shell. While for the electron yang berada ataupun located at the outer shell, we call it as outer electron shell. Okay, for example, electron, since dia cuma ada 2 elektron, N1 and N2, N1 we call it inner shell, and N2 we call it outer shell. In inner shell, we have only 2 electrons, and then this electron we call it as inner electrons. And for outer electrons in N2, kita ada 1, 2, 3, 4, 5, 6 electrons as known as outer electrons. This is how to determine the inner and outer shell electron. Another example, we use the potassium. Okay, in potassium, they have 1, 2, 3, 4 shell. Okay, and 1, and 2, and 3, and 4. And 1, 2, 3, okay, and 1, 2, 3, we call it as our inner shell. Okay, we call it as inner shell. While for number 4, okay, and as n is equal to 4, we call it as outer shell. So which means electrons that located in the outer shell, we call it as outer electron shell. Meanwhile, the electrons that located in the inner shell, we call it as inner outer shell, inner electrons. All right. Next, about the valence electron. Valence electron the valence electron is the electron that involved in forming compound, and also valence electron juga determine the location of elements in the periodic table. However, untuk yang about the location in periodic table tu, kamu akan belajar for the next chapter about the periodic table. Okay, untuk this topic, saya cuma bagi fokus on how to determine the valence electron in different electron, either from the main group's elements or in transition element. Okay, dekat periodic table, we can divide the periodic table into 1 to 3 types of groups. Okay, the main group, transition element, and the rare elements. Okay, for the main groups, okay, the electron valence are the outer electrons. So which mean I can write down another way. Valence electron is equal to the number of outer electrons. So itu adalah untuk main group element. Kalau kita tengok dekat periodic table, main group elements are located into part 1, group 1 and group 2, and part 2, group 13 until group 18. Group 13 and group 18 ni adalah non-metal. For group 1 and group 2 adalah metal elements. So the valence electron for main group's element is equal to the number of electron for outer electrons. Itu for the main group elements. While for the transition element, the valence electron is equal to the outer shell and any n-1d electron. So which mean I can rewrite the sentences. The valence electron of the transition element is equal to outer electron plus with n-1d electrons. Okay, what is the meaning of n-1 d orbital? Kita tengok for the next slide. Example here. Okay, for example, for phosphorus, okay, let's say kita ada phosphorus, electron configuration for phosphorus is 1s2 and so on lah, neon 3s2 and 3p1. Then kita draw the orbital diagram for phosphorus. Okay, we start with the 1s, 2s, 2p. Okay, 1s, 2s and 2p. And then kita masukkan dengan 3s and 3p. 1s, 2s, 2p, 3s, and 3p. Okay, then we fill up the electrons. Alright, so based on the orbital diagram, we can detect the inner shell electron, the outer shell electron. So based on the orbital diagram, 1s, 2s, 2p is the inner shell electron. Okay, inner shell of the phosphorus, and then for 3s and 3p orbitals is the outer shell. So from here we can determine the number of electron for inner shell electron and outer shell electron. Okay, for 1s, 2s, 2p, since it initial, so which means the electron that fill up in the orbital is the inner shell electron. Okay, and then while for the 3s, 3p, since it outer shell, so which means the electron that fill up in the 3s and 3p orbital, we call it as outer shell electrons. Since the phosphorus is located in the main groups, okay, phosphorus is located in the main groups, which is the non-metal. As I said, for the valence electron for the main groups is equal to the number of outer shell electron. So which mean if let's say an example in exam lah, how many the valence electron for phosphorus, you just count the electrons in the outer shell. So which mean 1 2 3 4 5. So outer shell 3s, right? Ini nucleus, ini N1, N2, N3. In N3, okay, dekat N3 dia ada 3s and 3p. Kalau N2, okay, N2 kita ada 2s and 2p. For n is equal to 1, kita ada 1s. So ini adalah dia punya outer electrons, outer shell electron. So dalam outer shell kita ada 1 2 3 4 5 electrons. So which mean the valence electron for phosphorus is 5 electrons. Okay, so this is how to determine the valence electron for phosphorus. Okay, next another example, scandium. Okay, with electron number 21. So this is the electron configuration for scandium. So we start with drawing the orbital diagram. Okay, first kejap for S2 kita for S2 and then 3D 3 4 5 3D 3 4 S. Okay, saya mau buat tu supaya dapat agak-agak dia punya space, and then 3D 3P 1 2 3, and then 3S 2P 1 2 3, 2S and 1S. Okay, fill up the electron 1 2 3, and then 3D this one. Alright, so let's say based on the orbital diagram, kita boleh lukis dia punya position like this one lah. Okay, dekat scandium dia ada nucleus, and then dekat scandium pun ada, since dia yang paling tinggi dia punya N is N4, bermaksud dia ada shell sehingga 4, 1 2 3 4. Okay, 1 2 3 4. Okay, untuk menentukan the inner shell, outer shell and electrovalence for the transition element, scandium ni adalah transition element kan. So untuk inner shell adalah, okay, untuk inner shell adalah shell yang berada pada yang di dalam lah, okay, yang dekat dengan nukleus, bermaksud outer shell of course pada N yang keempat, dan inner shell bermaksud pada N yang ketiga. Okay, kedua dan ke satu. Okay, N1 2 3 itu adalah dia punya inner shell. Okay, dekat N3, okay, kalau kamu tengok dekat sini, when N is 3, dia punya orbital yang ada dekat shell yang ketiga adalah 3s, 3p and 3d. 3s, 3p and 3d, bermaksud ini ni kita masukkan semua daripada 1s, 2s, 2p, 3s, 3p and 3d ni sebagai initial. Itu adalah initial bagi transition element. Okay, jadi elektron yang berada dalam inner shell ni adalah inner shell elektron. Okay, itu adalah initial elektron. How about outer shell? Outer shell bermaksud shell yang paling luar. Okay, untuk scandium ni, since dia ada yang paling since energy level yang paling besar, which is n is equal to 4, so bermaksud shell yang luar ni adalah n is equal to 4. Okay, when n is equal to 4, dekat orbital n is equal to 4 cuma ada 4s sahaja. That's why untuk outer shell electron, dia cuma based on the 4s orbital. So untuk outer shell electron ni, dia cuma ada satu sahaja. Okay, dia cuma ada satu sahaja. Dua elektron sahaja. Dekat sini outer shell electron ada 2 elektron sahaja. And then itu berkaitan dengan outer shell electron. Next, about the valence electron. Untuk valence electron, seperti mana yang saya cakap tadi, valence electron bermaksud untuk transition element. Valence electron dia adalah sama juga dengan the number of outer electron plus n-1 d electron. Bermaksud inilah outer electron 4s dan n-1d. Bermaksud kita merujuk kepada 3D orbital. Okay, n-1 bermaksud n ni yang paling besar, 4 minus 1. Okay, 4 minus 1 bermaksud ini adalah 3D lah kan, 3D orbital electron. 3D electron. So untuk detect dia punya electrovalence berdasarkan 4s orbital and 3D orbital, then baru kita dapat the valence electron for scandium is equal to 1 to 3 electrons. Okay, valence electron of scandium is equal to 3. Outer electron is equal to 2, and inner orbital, okay, inner electron is equal to berapa? 21 tolak 2, 19. Okay, kita tolak je outer. Okay, untuk dapat inner electron, kita cuma boleh guna berdasarkan this one outer. Since kamu sudah dapat outer electron is equal to 2, you just minus lah. 21 minus 2 is equal to 19. Itu cara dia untuk dapatkan the inner electron shell, shell electron, outer shell electron and valence electron for transition element. Okay, so kira ini adalah dia punya inilah. Okay, alright, another additional information. Okay, as I said, based on the valence electron, kamu boleh tentukan the position of element in the periodic table. So bila kamu tengok valence electron for main elements, okay, kita boleh dapatkan ada S orbital, S block, P block, D block and F block. For this topics, kamu akan belajar nanti on chapter next chapter rasanya about the periodic table. The last subtopic, which is the Ionic species. In this subtopic, I would like to explain how to determine the electron configuration for the Ionic species. Oh, sorry for the spelling error. Okay, from the previous slide, I already show you how to draw the neutral atoms or elements. For example, the sodium, potassium, the silicon, iron, and so on. But how to draw to write down the electron configuration when it change into the Ionic species? Alright, so this is the steps that you need to do to draw or to write down the electron configuration of Ionic species. Let's say we use the example of sodium ion and oxygen ion. Okay, so first step, you need to draw the orbital diagram for the neutral element. So before you draw, you need to write down the electron configuration lah kan untuk sodium and oxygen. So for sodium, since it has 11 electron, 1s2, 2s2, 2p6, 3s1, and the orbital diagram. 1, 2, 2s and 3s. 1s, 2s, 2p and 3s. So this is the orbital diagram for the sodium and oxygen electron configuration. 1s2, 2s2 and then 2p4. So which means the orbital diagram 1s, 2s and 2p only. 2p. 1s, 2s, 2p have 4 electrons. So singly first and then we pair up with the different orientation. Okay. Next step. The next step is to determine electron gains or loss for the neutral elements. Okay. So since given for A and A plus and B O2 minus. So this is the notes that you can use to determine either it lose the electron or gain the electron. If the cation, which is the positive symbol, it means the element lose the electron, while for the negative it means that the element gain the electron. So for sodium plus, which means it is the cation, so since it only mentioned 1 plus, so the total electron for the Na plus 11 minus 1, which means it only has 10 electrons in the sodium ion. Okay, for the oxygen ion, since it an ion, it will gain electron, and then which mean ini ada 2 kan, so the total electrons in oxygen ion at plus 2, which mean 10 electrons. Okay, 10 electrons in the oxygen ion. Okay, next step, in order to draw the orbital diagram and to write down the electron configuration, we need to do the addition of electron and remove the electron. So from the previous step, bermaksud di sini dia ada untuk sodium ion, dia akan remove 1 electron. Untuk oxygen ion, it will gain ataupun add 2 electron. Okay, then first for sodium ion, kita tengok for sodium ion, this is the original one. Okay, so the original one, 1s, 2s, 3p, 2p and 3s. 1s, 2s, 2p and 3s. So this is the original for sodium. Sorry. And this one, since in sodium ion, sodium plus, it remove 1 electron, so which mean we need to remove the 1 electron here. Okay, remove 1 electron here. So this is from the sodium, we can do as a sodium ion. So this is how to draw the the orbital diagram for sodium ion. And then for the oxygen ion, it add 2 electron. Okay, so the original, okay, 1s, 2s, 2p. Okay, this is the original for oxygen atom, the orbital diagram for oxygen. Then since in oxygen ion, it added 2 electron, so bermaksud kita tambah 2 electron into the orbital diagram, 1 and 2, then it become 2 minus. So this is how to draw the orbital diagram for sodium ion and oxygen ion. Then from the orbital diagram, then we can write down the electron configuration, the new electron configuration for sodium ion. So for electron configuration for sodium ion is 1s2, 2s2, 2p6. And for the oxygen ion, you just follow the orbital diagram. 1s2, 2s2, and 2p6. So step, write down the electron configuration for the ionic species. Sudah terawal step dia dekat sini. So this is how to write down the electron configuration. To write down the electron configuration, you need to refer to the orbital diagram, the new orbital diagram for the ionic species. Okay, so that's how to draw and to write down the electron configuration for ionic species. Why don't you try to do this one? Magnesium, bromine, and iron. Okay, iron. Okay, ferrum iron. Okay, so this is another example. Okay, let's say this one. For this example, okay, this one another example you can study by yourself. I think this is related to the previous chapter and this chapter. Alright, okay, so I think that's all for me for this chapter. Next, you can do your exercise, okay, and do the tutorial that I will give you later. So thank you very much and see you again. Bye. Assalamualaikum.